Good day, friends. Today let's try to solve some problems on impulse and conservation of momentum. And the problem goes like this. A moving ball collides with a stationary ball of the same mass. Find the angles of deflection of the balls after non-central elastic collision. So as you can see, we have two masses which are totally identical, but the most important catch of this problem is about this hit is non-centrical. So if our ball was somewhere here and it hit the center of this, the normal of the ball, then this problem would be easy. But right now, as you can see, that we are hitting non-central part of our second ball. And we need to find the angle of deflection, which is this alpha. Definitely we can imagine this situation like this. If our first mass comes with some velocity, 0, and then hits, of course it will be deflected upwards, and the second mass will go downward at some angle. And the angle between them will be some alpha, and we need to find that alpha. Okay, in impulse problems, the best thing that we should do is to work with vectors. Of course, we can do something about components, but the easiest way, mostly, not all the time, vectors would be very handy in this kind of situations. Okay, so in this situation we have three vectors, but the most important catch about these vectors, these are momentums. This is momentum 1, this is momentum 2, this is momentum 3, right? So why is it important? So we need to understand that these vectors do not depend only on the velocities, but the masses as well. So this would be not just velocity vector, but mass v0, and this whole thing would be our vector. This would be, again, mass v1, as you can see, yeah, of course, and this has to be mass and v2. This whole thing is a vector. Okay, and in this problem, that's not much of a case because I would suppose that these masses would cancel out. But in further problems where the masses would be different, we need to take into account that these are not just velocities, it's momentums. Yeah, we need to work with momentums. Okay, good. And first of all, you can see that this case, this part, is before the collision. Let me write it here, before. And everything what is happening here, yeah, let me take this problem statement a little bit lower. So everything what happens, everything what happens in here, yeah, after, these are the situations after the collision. Okay, and if you remember, we can add up some vectors with each other, and then we would have our resultant vector. We can see that the main vector that we have is this vector, and these two are created due to the first vector. However, we can go backwards, and that would be totally normal. Instead, what we should do right now is to take the last two vectors and add up to each other, and then we would have the resultant vector as our first momentum vector. And it still works, yeah? Let me take it even with arrow, yeah? Somewhere here, maybe here, yeah. This would be good, yeah, I like it. Let's take the second vector, which is this one. Let's put it here, yeah, somewhere. If you remember, yeah, let me take this, yeah. And even I would take out this thing, this would be enough. Also, this thing is not important, yeah, this would be enough. And our last vector is this one, and let me take it as well. Yeah, let me copy it and put it here. As you can see, it still works. So what we did is something like this. Let's call these our A vector. Yeah, let me choose some different color, maybe this orange one. Let's call these A vector. Let's call it B vector and C vector. And if you remember, we can add up vectors with each other. We definitely know that A is our resultant vector and B and C are just added up to each other. But in terms of the graphics, how do we add up vectors with each other? We take our B vector and then put to its head the end of the C vector, and then the initial point of the B vector and the last point of the C vector would be our resultant vector, which is our A vector. And as you can see right now, we can work with it pretty good. However, we have some angles like alpha, and where should we put it? In fact, we cannot put it somewhere inside of the triangle because as you can see, we have such kind of alpha, and this cannot be alpha. Yeah, this thing cannot be alpha, this thing cannot be alpha. Why? Because as you can see, it is not, it does not look like this one. This is not our alpha. Okay, so where should we put our alpha? Instead, we can just hypothetically continue this vector somewhere here. Yep, and then our alpha angle would be here. This would be our alpha angle. Okay, it is not inside of the triangle, but that's not a problem because we definitely know that this thing has to be in totality 180. And if that thing is alpha, then the rest part is 180 minus alpha. Okay, 180 degrees minus alpha. And right now we can use the law of cosines. If you remember the law of cosines, it states something like this. We can work with anything we want. We can work with this angle. If we know this angle, we can work with this, let's call some beta. If we know this theta, we can work with it. That's not a problem. We can use law of cosines in any case, but that's not much of a problem. The problem is about knowing how to work with it. So let me write it somewhere here, maybe. Law of cosines. Law of cosines. So how do we work with it? We take some angle, this one, for example, that we want to work with, and if we have vector against it, that would be our resultant vector that we are trying to work with. If we chose this angle, which is, as we have said before, this beta, then we would work with this C vector. If we work with this theta, then we would work with B vector. So that's something very important to note. Okay, and right now we're concentrated on this 180 minus alpha, and then our result would be our A vector. Okay, then in this case, it would be something like this. Let me continue with this one. Yeah, A vector squared, this would be B squared plus C squared, and minus 2BC cosine alpha. Yeah, this alpha is not exactly our alpha. Instead, let me take some theta maybe. Let me call some phi. Yeah, so the meaning of this phi is the angle that we are working with, and the resultant vector. Yeah, these two vectors are the rest vectors. Only thing that we need to know is this vector. And what is our A vector? Is the angle, is the vector that is against of the angle that we're working with. Right now we are working with this 180 minus alpha, and that's why our result would be A squared. If we worked with this angle, this beta, then we would have something like C squared, and then equal to something, something, something. Yeah? Okay, I hope you understood it very well. If you did, I'm truly happy, because it would be something very convenient to us. Okay, right now let's try to work with it. Our A vector holds the meaning mv0. That's why it must be something like this. Yeah, let me write it with black maybe. It would be m squared v0 squared, right? And then B vector and C vectors would be this m squared v1 squared plus m squared v2 squared minus, this is important, 2 and BC. As you can see, if we multiply B and C, then we would have mass squared, because we have here one mass, second mass. That's why let's write here m squared, and then v1, v2. This is also very important, v1, v2. And the angle would be not some alpha, because we are not working with this angle, we're working with this angle. That's why it would be cosine 180 minus alpha, I'm sorry. Yeah, this would be cosine 180 minus alpha. Okay, good. Right now, as you can see, we can take this masses out. Yep, this would be our common factor. As you can see, mass squared. We can take this out as a common factor out of the brackets, but instead we all know where is it going. We can just cancel those out. As I have said to you before, the masses would cancel out. That's why in this problem that's not much of important. It looks like we're working with only velocity vectors, but in further situations where masses are not the same, please remember to work with not velocities vectors but momentum vectors. This is very much important. Okay, good. What can we do? We see this thing. Right now, let me write result. This would be v0 squared. This is v1 squared plus v2 squared minus, yeah, this is important. Cosine, yeah, remember this thing. Cosine 180 minus alpha gives us minus cosine alpha. Yeah, good. Then this would be minus, and also minus here, then it would be plus 2 v1 v2 cosine alpha. Yeah, this comes from trigonometry. That's why, yeah, you can just remember this or understand its meaning. But right now, let's work with physics, not maths. Okay. Right now we have 3 unknown variables, and that's a little bit kind of a problem. However, let's do something like this. This is what we are doing here is, let me write it here. This is conservation of momentum equals to P final. Yeah, so this is conservation of momentum that we're working with right now. But also we can work with conservation of energy. And what would be our conservation of energy? The energy initial is kinetic energy of this entire part, yeah, and then this energy splits up into 2 halves, is the kinetic energy of this one and kinetic energy of this one. As you know, energy is scalar. It does not have direction. We don't have to work with some angles. That's why it would be something like this, something very, very simple. It would be just the kinetic energy of the first equation. Yeah, again, let me write it with black, and it would be mv0 squared divided by 2. This is kinetic energy in the beginning, and then it creates 2 kinetic energy. It splits into 2 other kinetic energies, which is mv1 squared divided by 2 plus mv2 plus divided by 2. Okay, yeah. This is plus, this is not minus, because direction is not important. What is important is the logic. And the logic is that this is the total energy in the beginning, and then it splits into 2 halves. Not exactly halves. It is not 50%, 50%. Somewhere it might be more energy, somewhere less energy. But the meaning is that this is one part, and this is the second part of this entire energy. And this is much more important. This is not minus, yeah? Okay, good. And as you can see, we have, again, common factors as 2 cancels out, masses also cancels out, and you can see that we have here, yeah, let me write it here, this is conservation of energy right now we're working with. Energy is not vector, that's why there is no arrow. This is initial, and then sum of energies, final. Good. right now we have such kind of result. Where is it? Yeah, v0 squared equals v1 squared plus v2 squared. Okay, as you can see it's something very good. Do you know why? Because here we have that v0, and here we have this v1, v2. Okay, let me take this thing and put it inside. And then you can see that we will have something like this, v1 squared plus v2 squared equals, again, this part, whole part, v1, v2 squared. This would be v1 squared plus v2 squared. And plus 2v1, v2 cosine alpha. Yeah, and as you can see, we can cancel those out, and then here at this side, you will have 0. This would be 2v1, v2 cosine alpha. But yeah, if we just leave it to the other side, yeah, to this side, then it would be also again 0, because everything multiplied or divided by 0 is 0. So it would be just 0 equals cosine alpha, which means that our alpha has to be 90 degrees. Okay, good. Well, right now we know that those two, if the masses are the same, only if the masses are the same, this angle of deflection has to be 90 degrees. Has to be. Okay, that's good. That's very something convenient. But if it was not the same mass, but different masses, then there is no any guarantee that these had to be 90 degrees. Okay, right now let's try to work with something very similar. Right now we would have probably the same situation, but a little bit further. Two identical particles move toward each other at an angle alpha with initial velocities v1 and v2. After an elastic collision, one of the particles has velocity u1, yeah, but instead I've written it as v3. Find the angle at which they separate. Okay, this is very interesting problem. As you can see, we don't have the fourth velocity. Yeah, let me note it with different color, maybe with orange again. Let's write as v4, and let me note it with, I don't know, red probably. No, not red. Not the best idea, but okay, let's keep it green. Yeah, let's keep it green. The main thing is it is visible. And we don't have that v4. We have v1, v2, v3. We have that two identical particles, which means that their masses are the same. They move towards each other at an angle alpha, which is here. And we need to find angle at which they separate, which is this beta. Yeah, we need to find this beta. We're interested in this beta. Okay, good. Okay, it's the very same principle. Yeah, we have here the situation. Okay, let me take it a little bit lower. The problem statement, we have already read that. And let me note here, yeah, everything what happens here before and everything, yeah, before the collision. And here we have everything what happens after the collision. Okay. And again, we have to work with vectors. Here we have 4 vectors, as you can see, but instead I would give you some suggestion to work with the situation only before and then only after. So the sum of these two vectors gives us some resultant vector, right? And the sum of these two vectors would give us also some kind of resultant vectors. And physics tells us that these resultant vector has to be equal to these resultant vector. The logic behind it is that these vectors is, yeah, again, let me note it with, let's write it as P1. This is our P2. Let's call it some P3. And let's take here P4. Yeah, these are momentums. These are not just velocities. The mass multiplied velocity. And okay, this one is vector as well. So the logic behind it is that if it has some momentum, this has some momentum, the resultant momentum cannot be greater or less than this resultant momentum unless it is some, I don't know, inelastic collision. Yeah, because we know that in inelastic collision, some of the velocity might be lost due to deformation, due to heat, I don't know, or other type of energy loss. And when we lose energy, we're not losing energy, but our energy is converted to another type of energy, and then we lose some part of the kinetic energy in the beginning. But in this case, if it is absolutely elastic, then the velocities can lower, yeah, one of the velocities can get lower, but the second one has to get higher, and that is exactly what we call conservation of momentum. Okay, then the logic goes like this. Let me take this vectors again. Yeah. Okay, let me take it with arrows together. Oops, excuse me. Yeah, like this, good. And right now we can do again that logic. Okay, let me take all these things, and we can do something like this. It does not matter. We can do it here or here because the resultant vector would anyway will be this part. Yeah, let me take again this. This would be our resultant one, and let me even take something thicker. Yeah, so you see it very well. This is our resultant vector. Okay, this is our momentum 1. Oops, momentum 1. This is our momentum 2. Yeah, and this is our resultant. Yeah, let's write it as momentum result 1. Yeah, okay, good. And if we take these two vectors, their resultant vector has to be the same, in fact. Yeah, let me take the arrows as well. Yeah, we can do it somewhere here. It's okay. Let me take this out. We don't need it right now. Not here. Yeah, we can take it and put it. It does not matter. We can do it like this. We can do it like this. And it's okay because the main logic when we add up two vectors, one of them, does not matter which one of them has to add up to the initial point of the second one has to connect to the final point of the first vector. And that is exactly what is happening here. And as you can see, those two vectors, yeah, this one, I can take it and put it here. Again, it works. Yeah, of course I have drawn it so it would be something very convenient to me, but the logic would be the same, and it is correct drawing. Then it would be our momentum result 2, but we know that momentum result 1 has to equal to momentum result 2. Yeah, those two resultant vectors has to be equal to each other. Okay, the very same logic goes here. So we have some alpha angle. We apply the very same logic. If we continue this line here like this, and also we can continue it here, then I hope that you don't get distracted. This would be our alpha angle as the initial, this one. Yeah, we have done it in the previous problem, so I hope that you don't get distracted. Yeah, let me even take it a little bit lower so you don't get distracted. Yeah, like this maybe. Good. This would be our beta. The very same principle, yeah? I hope that I don't have to explain why. The very same principle, this has to be 180 minus alpha. This has to be 180 minus beta. And the very same principle goes here. Well, again, this one and this one has to equal to each other. Conservation of momentum works in here, yeah? So if we do it with vectors, it would look something like this. Yeah, let's write for the first one, the first situation, then I would write it for the second situation. Yeah, so the momentum, let's write it as P, yeah? P resultant 1 squared equals to P1 squared plus P2 squared, then minus 2 P1, P2. P means momentum, just we can open this up as mass multiplied velocity, but right now I don't want to, because then you would see why, yeah? This would be cosine, and our angle that we are working with right now is this one, 180 minus alpha, because our result has to be this one, right? So this would be 180 minus alpha. The very same principle goes for this one. We're working with this angle, that's why this has to be our result. It would be our P resultant 2, squared. It would be P3 squared plus P4 squared minus 2 P3 P4 cosine, but the angle that we are interested in is 180 minus beta. Okay, good. And as I have told you, these two things have to be equal. This thing and this thing has to be equal to each other. That's why we can take these two things. Yeah, let me take it entirely and make it equal to this thing, because the resultant vectors has to be equal to each other. Okay, yeah, and let me draw everything in black. Yeah, okay, good, I like it. Okay, I hope that you see where is it going. The masses are identical. It was set here, two identical particles. The very same principle goes, but I would open this up as you like it, because I hope that you don't get distracted, and it is the most important thing. This is mv1, this is squared, plus mv2 squared, minus 2 mass squared, because one of the masses comes from P1, the second mass comes from the P2, and the masses are the same, that's why they would be squared. But the velocities are different, that's why it would be v1, v2, and as I have told you before, this thing, cosine 100 minus alpha, 180 minus alpha, it is minus cosine alpha, yeah? And as you can see, minus here, it would be plus, that's why I can write it here, plus cosine alpha. Good. In this side, we would have the very same thing, m squared v3 squared plus m squared v4 squared minus 2m squared v3 v4 cosine 180 again gives us minus cosine beta in this case. That's why minus and minus, yeah, this minus and this minus would give us plus. This thing has to be plus here. This would be cosine beta. Okay, good. And as you can see, we can take these masses as common factor to outside, and the same thing happens here. The very same masses come out as common factor, and then you definitely know where is it going. Just cancel. This is cancel. Good. Okay, what we have here is v1 squared plus v2 squared plus 2v1 v2 cosine alpha equals v3 squared plus v4 squared plus v3 v4, okay, 2, yeah, I forgot 2. This is 2v3 v4 cosine beta. Yeah, good. This is what we have so far. However, again, we can apply here the law of conservation of energy, the energy before, yeah. Let me take again this violet one. The energy before is conserved, and then it would be equal to energy after the collision, if it is absolutely elastic. This is the most important part. Okay, and the energies before is the kinetic energy of this one, kinetic energy of this one, and then the kinetic energy of this one, kinetic energy of this one. So we would have something like this. Our conservation of energy would be mv1 squared divided by 2 plus mv2 squared divided by 2 equals, yeah, because their energies add up, and then they create mv3 squared divided by 2 plus mv4 squared divided by 2. And again, as you can see, the common factor, let me take red, just 2 cancels out, masses cancel out, and you can see something very good. This is v1 squared plus v2 squared gives us, as a result, v3 squared plus v4 squared. Remember this thing, this is very important. This thing gives us this thing. Okay, why is it important? Because you can see it, that it is here. So this is our v1 plus v2 squared, yeah, this thing. We can substitute it with v3 squared plus v4 squared, and then you can see that we can cancel those out because they are equal to each other, this thing and this thing. Yeah, yeah, let me first note it with green so you can see it better. Yeah, those two things are equal to each other. These things are equal, that's why we can take them as some, I don't know, some letter A, for example, yeah, and we can cancel those out. That's not much of a problem. And then we would have here 2v1 v2 cosine alpha equals 2v3 v4 cosine beta. Okay, good. As you can see, v2 and 2 goes out, and the meaning of our beta would be something like cosine beta would be equal to cosine alpha, and here it would be v1 v2 divided by v3 v4. Okay, good. But the problem to it is that we don't know the meaning of v4, but we can take it for conservation of energy from here. Then it would be v1 squared plus v2 squared minus v3 squared would give us v4 squared. And logically, if we take all this thing, if we take all this thing into square root, then we would have the meaning of the v4. Yeah, this is the meaning of v4. Okay, and we can put it in here, and then we would have our final answer, but let me write it here, cosine beta. Yeah, if you want to find beta itself, you just take our cosine. Yeah, and it would be cosine alpha, and inside of the brackets, it would be v1, v2, and here we have v3, and inside of the square root, it would be everything what we have written there. It would be v1 squared plus v2 squared and minus v3 squared. And as you, and let me close the brackets. Let me make it a little bit upper. Yeah, and then you can see the result of this problem. Yeah, this is our answer. Yeah, as you can see, we were given with v1, v2, v3. We're not given v4. Yeah, we gave meaning to v4, but at the end we got rid of it, and then we had only these values inside of our answer. And alpha is also given. That's why everything is known. Yeah, that is a small analysis and problem solving on conservation of momentum and impulse. I hope it was clear to you. But if it was not, you can write me privately. And yeah, always be free with me. Please text me, and then I will explain as much as I can. Yeah, thanks for your attention.